So central tendency, we've already seen these numbers. I'm not going to spend a lot of time on it, but central tendency, where is the center of your population? The middle of the process. Central tendency is a statistic that summarizes the entire data set with a single value that states the center. And it's 3 values that actually do the same thing. They're not calculated the same way, but they have the same intent. We have the mean, which is the average of the population. We have the median, which is the midpoint of the population. And then we have the mode, which is the most frequently occurring value. Each one of those is considered a measure of central tendency, but only applies in certain circumstances. And we've already seen that. Remember the difference between normal and what's the other type of data? Skewed or non-normal data. Okay, for normal data, what would be my central tendency measure? The mean, the median, and the mode. Isn't that interesting? All 3 would apply. But the one that we would defer to in terms of continuous data would be the mean. The mean would be my estimate of the average. But when the mean, the median, and the mode are the same, what does that tell you about the underlying distribution? It's normally distributed. Any gaps large enough would suggest that the data is not normal. So the mean, commonly referred to as the average. The symbol for the sample mean, from the sample distribution that you've taken from the population, randomly I hope, is called X bar. The symbol mu is the symbol for the entire population. Very rarely will you be dealing with population data. Most of the time you're making decisions based on sample data. So often we're using the X bar. We add the numbers together, we simply divide by the number of data points. We learned to do that in grade 4 or some equivalent like that wherever you came from. And it's considered the point of balance for the data. And I think I might have mentioned that before. You ask a simple question, what is the purpose of the average? Explain that to me. I mean, why do we calculate the average? Why is it important? What's the relevancy of the average? Yeah, but why would we want to know what the average is? What is the significance of the average when you think about the population?
We just use the change of error.
Okay, not. Yes.
Do you think it's representative of what the results would be in the overall population?
No, even the average of the population, what would the average represent if you thought about it?
Majority?
Well, you would think the majority would cluster around the average, a little bit like, buffaloes in a field being threatened. They'll all kind of huddle together. Cows in the field will get together, right? Huddle for warmth, maybe. But what is the purpose of the central? What is the purpose of the mean? It's a measure of central tendency, right?
Yeah.
So what's the purpose of the mean? To tell you where the center is. So if I was in the center of a population and I was in the mean, and I looked that way, how much of the population would I see? 50%. So it's the tipping point. It's where the center of the population is. That's the only reason we calculate the mean.
What's kind of the median, though?
What's that?
The median.
The median does the same thing. If it's a normal distribution, the mean and the median are the same. But if it's a non-normal distribution, we can't use the average because the average is no longer an indicator of that 50-50 dividing point. The point of balance, right? The median in a non-normal distribution, the balance would be here. It would be balanced right on top. But if I use the average as my indicator, what would happen is the average would be here, and it wouldn't be balanced anymore. It would fall because more than 50% would be below where my average is being calculated. Right? So that is the purpose of the mean, is to simply figure out where the center, where 50% of the population resides above and below that value. So is the mean adequate for us? If you add up these numbers, what's the average of this number, these set of numbers? What would you get? Take a wild guess. 12. Yeah, 12. Okay, so if we took this set of numbers, what would be the average? 244 or something stupid like that, 344, I have no idea. It would be a big number. Why the difference? I only added one other data point. Because it's an outlier. So right away, when you've got outlier data in your data set, the outlier data, the skewing effect, is pulling your average artificially in that direction. So if I calculated the average, it's not really the tipping point where I find 50% of the data on either side. It's been moved artificially because of that skewing and that outlier. So all of a sudden now the mean is no longer a relevant term to tell you where the midpoint of your data is. So where do we go? We go to the midpoint calculation, the median. The median is simply the middle value of a set of values or set of numbers ordered from lowest to highest. The median ensures that one or a few abnormal values do not skew the central tendency calculation for that data set. I mean, this is really important when you think it's so simple. Why do we calculate the average? To find out where the 50-50 line is in terms of the data set. And now all of a sudden, now when we're looking, I understand why the median is used now. If I calculate the median in a skewed set of data, it'll still be balanced. But if I use the average, it falls down. It's no longer balanced because more than 50% of the data is on this side now. If you're calculating, and you know, we show the calculations, but boy, do we really need to? I mean, put the data, press a button, and it tells us. So if it was calculating, it's really simple. When you've got an odd set of numbers, lowest to highest, you take the one that's in the middle. If you've got an even set of numbers, you take the two that are in the middle beside each other, add them together and divide them by 2. That's how the median is calculated. But we don't calculate much anymore, we just let the computer do it for us. What's important is remember why we're calculating it, not how we're calculating it. So once again, we got a set of data here, calculated the median of this data set, what number would you get? 12. Calculate the median of this set of data. You get 12.
Well, yeah.
You get 12, because all I've done is I've added an outlier to the set of data, but the median's still going to stay where it is. The median is going to be centered around these two numbers here, because these are the midpoints of the data set. The last is the mode. The mode is the most frequently occurring. We've seen the mode when we did our histograms. This is a histogram on its side, you know, but normally when we look at histograms, we see them in this fashion. This is kind of rude. It looks like a couple of hands giving you the whatever symbol that might be. Yeah, I've had enough of this course, you know what I mean? Anyhow, this would be considered bimodal. And it means that you've got more than one mode. You've got two modes going on. But I want you to remember that bimodal doesn't always have to be like that. You don't have to have both modes exactly the same. This would be considered bimodal data. But you can see here by looking, hey, this is real good. If you could only get high on this stuff, it would be even better. I told you my story about the Gestetner, right? Gestetner? You remember that? Yeah, Gestetner. I got all kinds of stories. Okay, not a lot of brain cells. So, there's my distribution there. And there's my distribution there. This could be the result of mixing two distinct populations, non-homogeneous populations. But when we do data analysis, we could actually do that. When I got the call tracking data, they throw all the numbers together. I immediately tried to separate them out because we've got, at a minimum, we got two types of calls, general inquiry and assessments. And I bet you within assessments, if I broke down the nature of the assessment being done, it could be broken down into smaller populations as well. And if I took the general inquiries and broke them into the complexity of the inquiry, those two would have their own little mini populations in terms of distribution. Yet when the municipality is analyzing it, they're throwing them all into one big pot and saying, here's our average wait time is 15 minutes. I'm thinking, that's not true. Those numbers are skewed. Yes?
I just also want to add too, when you're looking at a process map, you're looking at your data, it looks like that. It could be two different processes mixing.
Absolutely, absolutely. Yeah, you've got more than one population at work. I can tell you the average of this, right? I could calculate the average. But could I, if I gave the average for this population based on all, it wouldn't be relevant for this one, and it wouldn't be relevant for that one. The average is calculable, but it's of no relevant value, because I can't use it against any of the populations. So for me, the analogy is simply taking all of the data, putting it in a big pot, stirring it around like mulligatawny soup or stew, and then telling you what the average acidic content is. I mean, it doesn't make any sense. I can give you a number, but so what? So that's the mode. So the key lesson here is that, you know, in this example, we've got the departments complaining that their salaries are not in line with the market value. So the company goes out and does an analysis. What are you talking about? You know, we're paying on average $45,000 a year for people, and that should be okay. But the people that are in the department said, no, we did a bit of Six Sigma here. The reason that our average is so high is because we got the high paid salaries in there pulling the average north. Let's take that out of the data set, and we'll find now that our actual salaries are well below the industry average. So I mean, a very simplistic example, but that's where the average can have a very much a distorting effect. So that's the first part. I mean, central tendency is really, really important. When you look at these two sets of data, if you calculated the average, what would you get for both sets of data? We got 20 more minutes of this pain, and then you can go home.
Maybe that's 5.
Yeah, something like 5, right? But, so what is different about these two sets of data? If you look at them.
The variance between the numbers.
The variance, the spread, the dispersion. This one ranges from 1 to 9. This one only ranges from 3 to 7. A very simplistic example, granted, but in both cases, the central tendency, the mean and the median, are the same. But what's different about this set of data is the amount of variability. And so now as Six Sigma thinkers, and again, for you in the service industry, for me, that's one of my competitive, well, I would call it a competitive advantage. It's almost like a weapon. If you go into the service sector, they don't even get variability. They're feeling it every day. Their customers are feeling it every day, but they're not measuring it. So, I mean, when you go in there with a notion of looking at variability and you show a run chart and start pointing out the variation, it's almost like you're a magician to them. You say, well, no, hang on. I'm not doing anything special here. This process has been telling you this for the last 10 years. And your employees have been feeling it for the last 10 years. No one's bothered quantifying it. So all you're doing is putting a face to what people have been feeling. And once we do that and we quantify it, we're one step away from understanding how to control it. Measures of variability. There's a number of measures of variability out there. I want you to just use the analogy that, you know, at the end of the day, I want to get to Union Station. For me, Union Station is standard deviation. That's the number I'm looking for. I want that one number that's my yardstick to tell me how wide a process is distributed, right? Because we know that in a normal distribution, how many standard deviations on either side to the tail? 3, plus or minus 3. So what's the natural tolerance of a normally distributed process? Natural tolerance is 3 plus 3, 6 standard deviations. That's natural tolerance. So most processes would be distributed that way. So when people talk about natural tolerance, what they're talking about is what is the spread of your process? What's the lowest value and the highest value when you consider the entire distribution? That's Union Station for me, because that's going to be my universal yardstick for assessing and comparing variability. However, to get to Union Station, I got to do a few calculations. So it's a little bit like stopping at Maypole, stopping at the different stations on the train to get to Union. So let's take a look at some of the stops first. Range. That's it. You okay? The statistics is getting to you? I thought so. Yeah. I've only had 3 or 4 people vomit in the class because of statistics. We try to save that for the final exam. It's far more fun. Okay, so in this case, the range is very, very simple to do. We've got a lowest value of 15, a highest value of 72, so that we know that the range of incoming calls is 57, right? So that gives us a sense of variability, but it's not a really good measure for us. We want something a little bit more precise than that. Now, when we're doing box plots, remember when we did some box plots? A box plot looks like this. Okay, there's the box plot. What area is this called? This whisker is called the what? In terms of quartiles? That's your first quartile. That's your second. This is your third. And that's your fourth. This area in here is called your interquartile range. It's your second and third quartiles. If this was normally distributed data, something that looks like this, that's the comparison. It's kind of the center part of your distribution where you're going to see most of your population. Right? If you're going to design clothes, design meals, the size of the meals, for instance, Predrag's in the food business, the portions would be designed based on the normal population. So obviously knowing where that is and the width of it will tell me the range of values in terms of overall portion that I'm looking for. So the interquartile range would obviously give me a sense of the amount of variation and where we're going to find most of our population. At least 50% of it, right? Because each one of these represents 25% of the population. That adds up to 100% of the population. 25% of the population will be found, well, look at it this way. 25% of the population is found between infinity and here. Another 25% is found in this area, another 25% is found in this area, and then another 25% is found in that area. So, of course, in its normal distribution, we think of plus and minus 3 standard deviation, and we use that as an estimate of the area under the curve. It's much more precise. But the interquartile range is still a fairly good measure. The next step is to actually calculate something called variance. Now this is important for engineers. Isn't it, Marco? Variance is additive, which is kind of cool, is that you can add variance together to come up to total variance. So that's one of the properties of variance and why engineers need this number. Standard deviation is non-additive. You can't say, oh, this one is 2 standard deviations, this is 3, so that means 5 standard deviations. That's not the way it works. Because standard deviation has a square root in it. It's in the calculation. We'll see that in a short while. So the variance is something that's important from an engineering perspective, but not when we're trying to relate it back to the product that we're observing. So for instance, if we were able to take this funky formula and apply it to these numbers right here, we would find that the variance of this set of data is 233.6. Which is a kind of an abstract number when you think about it, because if I said to the person that's running the call center, I said your average number of calls is, say it's 40, with a variance of 233. 233 is not the same unit of measure as number of calls. So it's like apples and oranges. I need that variance number to actually do design engineering, but I can't mix it in with my statement around the average because they don't have the same unit of measure. So that becomes a bit of an issue for me. So is variance enough? And again, I'm not spending time telling you and saying, hey, you got to remember how to do this formula here. You know what? I tell you, there's the data set, put it into Process MA, press the button, there's your variance. What does variance mean? You can look it up in a dictionary somewhere. Engineers know what it means. But it is a measure of variability, and that's important. So, it's the average of the squared deviations. That's what variance gives you. It's the squared deviations, average of those, to tell you approximately how much variability you've got in an underlying process. But it's hard to explain that number when it's not in the same unit of measure as the thing that you're measuring. So that's where standard deviation kicks in. Because if you look at the calculation here, sigma squared is variance. So what would sigma be? The square root of variance. To get rid of that squaring, I'll take the square root. I'll take the square root of this number, and it's going to actually give me what the standard deviation is. And that's the calculation. This formula here, if you'll notice, is the same as this formula here, but just with the square root added. And that's the calculation for standard deviation.